All right, for this next example, we're going to go through and use the convolution theorem to go through and solve an integral equation. And the idea is that we're trying to find a function y of t that makes this equation true if you were to substitute it into the equation. This is very similar to a differential equation where we use derivatives, but in this time it's integrals. So the first thing you'll notice in this problem is that this integrand, the stuff inside the integral, looks a lot like the definition of convolution. We see that we've got an integral from 0 to t, and we've got the product of two functions integrated with respect to some variable d tau. And so the idea is to first rewrite this using convolution. So the idea is that this y of t is being added to the convolution of the function t with the function y of t, and that result is equal to 1. We can now take Laplace transforms of this equation, and when we do that, we end up with big Y of s plus the Laplace transform of t, which is 1 over s squared. Now multiplication, regular multiplication, Laplace transform of y, which is big Y of s, equals the Laplace transform of 1, which is 1 over s. And now we can go ahead and solve this equation for big Y of s. We first will factor. So we have a 1 plus 1 over s squared is equal to 1 over s. Then we will get common denominators. So y of s is equal to s squared plus 1 over top of s squared. And that's multiplication over here, not equals. So again, that's times is equal to 1 over s. We can now divide both sides by the s squared plus 1 over s, which is the same thing as multiplying by the reciprocal. So when we do that, we end up with big Y of s is equal to the 1 over s already there, times the s squared, that should have been a square there, over s squared plus 1. You'll notice that we can lose one of the factors of s, and we end up with big Y of s is equal to s over s squared plus 1. And we should quickly recognize that that is nothing more than the Laplace transform of the cosine function. So if we take the inverse, we get little y of t is equal to just the cosine of t. And that function right there is the solution of this integral differential equation. If you were to actually take this function cosine of t and substitute it back into the original equation, it would make a true statement.